Thank you. I have a conjecture that this will not last an hour, but we'll see. So it's been a long time for many of you, so I'm sure it'll be okay if I end early. Okay, so a lot of what I was going to do, Paul is doing, but let me just give you a brief recap on Adplus. So theta is the supremum of the ordinals alpha onto which you can map the reals. And then we have the Adplus axioms, ZF plus DCR. If you have a continuous map from gamma to the omega to omega to the omega and a set of reals, then the induced game on gamma is determined. And then this is every set's infinity Borel. Paul hasn't quite defined that yet, but this is equivalent to that assertion in the context of AD. So if you assume AD and DC for reals, a set of reals is infinity Borel if and only if it can be constructed from the reals and some set of ordinals. And the motivation of Adplus, it's not a strength, it's a structural strengthening of AD, and it's not meant to be a strong theory compared to AD. And by the Moskowakis coding lemma, Adplus is downward absolute. If Adplus holds in V and you take an inner model containing all the reals, then in that inner model, Adplus holds. Okay, so why Adplus? There are a lot of reasons. The original motivation was to strengthen structurally AD and recover many of the consequences that AD has for L of R. So L of R AD provides a complete analysis about L of R. In the sense of Shala, AD L of R is a semi-complete axiom for L of R. But much of that analysis uses the smallness of the model L of R, the fact that it's the minimal model of ZF containing the reals and the ordinals. So here's one example. Paul has kind of mentioned this. So let M delta 2, 1 be the union of all the transitive sets M, such that M is coded by delta 2, 1 relations. So you have an equivalence relation on the reals, a binary relation that respects that equivalence relation, each delta 2, 1, such that these are isomorphic. And then you can define M delta 2, 1 light face, where you just require that these sets are delta 2, 1 light face. Okay, so this is the generalization of the Martin-Steele theorem, which Paul mentioned, in L of R. So sigma 2, 1 has a scale property. So assume Adplus, and sigma 2, 1 has a scale property. Suppose X is sigma 1 of R definable in LFP of R. If X is non-empty, then X has a member in M delta 2, 1. And then you actually get that the boldface M delta 2, 1 is a sigma 1 elementary substructure of LFP of R. That's the generalization of the Solovay basis theorem. So this fact is true in L of R, just in ZF. So the basic theorems of L of R, the scale property and the basis theorem for sigma 2, 1, are both Adplus theorems. So that's... Okay, so let me give you another example that generalizes a result I mentioned last week. So there was the Kekres-Martin theorem for pi 1 omega plus 1, which was an application of fine structural techniques within descriptive set theory. Let me remind you what that theorem was. So the setting now is PD, boldface, and you let T1 omega be the direct sum of all of the trees you get from projective scales. Then you let eta be the least admissible relative to T1 omega. So L eta of T1 omega is a generalization of L omega 1 ck. And then the reals of L eta, T1 omega is just the Q at pi 1 omega plus 1. That's the generalization that the reals in L omega 1 ck are hype. the reals intersect L eta of T1 omega is actually in L eta T1 omega. That, of course, is not analogous to hype. And then you get the Kuhnen, the Kekres-Martin theorem. So let, again, eta be the least admissible. Take a subset of the Q set. That's just the reals of this model. Then the following are equivalent. X is light phase pi 1 omega plus 1 definable. X is sigma 1 omega plus 1 definable within the model. Now this is just Spector-Gandy, but this is the new ingredient. X is sigma 1 definable in this model from T1 omega as a parameter. And the difficult direction is to assume 3 and deduce 1 or 2. A priori, using T1 omega as a parameter, you might be able to define something more complicated. Okay, so what does Adplus do with this theorem? This heavily used Rudemeyer stacks in fine structure. So the proof of this theorem seems like it's rooted in low levels. But in fact, it's not. And that's where Adplus comes in. So assume A is a set of reals. Let's say that A is strongly projective-like if sigma 1n plus 1 of A has a scale property for some n, the light phase. Well, then we can define T1 omega of A exactly as we defined T1 omega. We just use sigma 1n in A formulas in place of sigma 1n formulas. And then there's a Q structure that follows from the Kekres-Martin-Solovay theory, and the Q set relative to A is a set of all x such that there exists a y, x is recursive in y is a pi 1 omega of A alpha singleton for some alpha less than omega. This is the direct generalization of Q theory for pi 1 omega plus 1. And then we can look at the least admissible relative to the tree, and we get that the reals constructed by the first admissible from the tree is exactly the Q set, and that, in fact, the reals intersect that structure is a member of the structure. Remember, when you construct up to the least admissible, it's not obvious that the reals you get are actually a member of the structure. It's false with L omega 1 ck. And then we get the Kekres-Martin theorem. So T1 omega of A is naturally a subtree of omega cross delta 1 omega of A. This is just a soup of the lengths of the pre-will orderings, which are projective in A. Light face or bold face doesn't matter because we're at a projective level. And so we can suppose A is strongly projective-like. This is the Adplus theorem. Let eta be the least admissible relative to that tree. Suppose X is a subset of the Q set. Then the following are equivalent. It's pi 1 omega plus 1 in A. It's sigma 1 omega plus 1 in A definable within the model. That's Spector-Gandy again. But then we get the equivalence with sigma 1 definability with the tree as a parameter. So this just indicates the power of Adplus. What's going on here is a technique, it's a fine structure, it uses fine structure, but relative to a class of structures that are known as hybrids. Okay, so that's just indicating the utility. In fact, the analysis shows a bit more. I didn't mention that last week. This is take any ordinal less than delta 1 omega of A, then the power set of alpha intersect the model is actually in the model. So that generalizes the fact that the reals are in. And again, that's not obvious because we're only constructing up to the first admissible. Okay, so basic notions, you can forget about all of that now. Paul has defined some of this, but let me remind you, Suslin sets and Suslin cardinals. A subset of that was supposed to be a set of reals, A subset of omega to omega is lambda Suslin if it has a lambda scale. Lambda is a Suslin cardinal if there's a set A such that A is lambda Suslin and not delta Suslin for any delta less than lambda. Having a lambda scale is the same as being the projection of a tree on lambda. So the scale is a different way of viewing being Suslin, and it fits a little bit better with descriptive set theory. So omega and omega 1 are Slim cardinals. The set A that witnesses that omega is a Slim cardinal is a complete sigma 1,1 set. And the complete sigma 1,2 set witnesses that omega 1 is a Slim cardinal. Now, if you look in ZFC, then, or if the reals can be well ordered, then C is a Slim cardinal. It's the largest Slim cardinal, and every infinite cardinal less than C is a Slim cardinal. And that's trivial. So in the AD plus setting, or in the AD setting, the Slim cardinals are in some sense the true generalizations of the cardinals in ZFC. But there are other cardinals. Okay, so AD versus AD plus. Suppose A is Slim, assume A. I'm going to work in ZF plus DC for reals almost exclusively. Suppose, it doesn't mean that all the theorems require DC for reals, but dropping DC for reals raises all kinds of issues. Suppose A is a set of reals and A is Slim, that means it's lambda Slim for some lambda. Then if we go to the inner model L of A and R, it's a model of AD plus. Let gamma be the set of all Slim sets. We're working in just AD DCR. Paul mentioned this theorem. Then if you construct from all the Slim sets, that's a model of AD plus. If gamma is not equal to P of R, so if not every set is Slim, for example, then L of gamma and R is a model of ADR. Okay, so ZF plus DC plus AD plus not AD plus, if consistent, is very strong. It implies the consistency of ADR. And I guess theorem, I should have stated that as let gamma be the set of all A such that L of A and R is a model of AD plus. Okay, so if you assume ZF plus AD plus DC, and now the DC is not as necessary for the proof, then the following are equivalent. Every set is Slim, ADR, and uniformization. I think Paul will be headed towards some version of that theorem. The DC should not be necessary. Corollary, ZF plus DC, assume ADR, then AD plus. And the conjecture, of course, is assume AD, then AD plus must hold. But for much of what I'm going to do, and for a lot of the theory, AD plus is really, the inner models of AD plus are the models one is really interested in, because they're the ones connected to fine structure and large cardinals. Okay, so now we're going to look at HOD, and mostly in the context of AD, but the story begins with Solovey's result that if you assume AD, then omega 1 of V is a measurable cardinal in HOD, and that's because the club filter is an ultrafilter, and Solovey's theorem gave the first connection between AD and large cardinals. Now, if you assume AD plus, you get a stronger theorem in some sense. If you assume AD plus plus V is LFP of R, then omega 1 of V is actually the least measurable cardinal in HOD. And the hypothesis that V is LFP of R is necessary for this theorem. So now we're going to be not only assuming AD plus, but for the most part, assuming V is LFP of R. And the reason is we're going to be interested in HOD. And if you drop the LFP of R assumption, you can code information into HOD by coding into the power set function above theta. And so not only that is how you show that that the hypothesis V is LFP of R is necessary, even if you assume AD plus. Okay, so omega 1 is, in the canonical setting of AD plus V is LFP of R, omega 1 of V is the first measurable cardinal of HOD, so it's the first genuine large cardinal. And if you go up to theta, now this is actually an AD theorem, and you don't need the LFP of R assumption. Theta is either a Woodin cardinal in HOD or it's a limit of Woodin cardinals in HOD. So this suggests an inner model test question. Suppose phi is a sigma 2 sentence which defines a large cardinal axiom, like huge cardinal, rank to rank, supercompact up to an inaccessible. Assume AD plus and V is LFP of R. Can HOD satisfy phi? So for any intermodal, where we have intermodal theory, the answer is yes. Doesn't seem to be any way to get a positive answer here other than develop intermodal theory. If, on the other hand, one could prove that some sigma 2 expressible large cardinal axiom could not hold in HOD, that would be an anti-intermodal theorem. Okay, so where should we be looking for large cardinals? Well, assume AD plus and V is LFP of R. Suppose kappa is a measurable cardinal in HOD, then kappa must be less than theta. That's basically because HOD is L of a subset of theta. So if you assume AD plus and V is LFP of R, the large cardinals of HOD can only occur in the interval from omega 1 to theta. So we want to break that interval down, and that's the Solovay sequence. So the Solovay sequence is the approximation to theta. Now I'm going to give the definition in AD plus, which allows one to avoid the wage hierarchy and gives a more elegant definition. But this is not known to be equivalent to the definition in AD. So theta 0 is the supremum of the ordinals such that you can map the reals onto the ordinal by an OD set. Theta, this is now where it's different. Theta alpha plus 1 is the supremum of the ordinal such that you can map the power set of theta alpha onto psi by an OD map. So there's no picking a set of wage rank theta alpha here. Theta alpha, you take limits at limit stages, and you stop when you reach theta. So this is a sequence of approximations to theta in the AD plus context. It could be that theta 0 is theta. That's the case in L of R. Okay, so now we can try to analyze these approximations to theta from a number of perspectives. First is from the perspective of Slim cardinals. So this is I'll call it a cabal theorem. Assume AD plus. The Slim cardinals are closed in theta. Theta alpha is a Slim cardinal for each alpha less than omega. That's the length of the Solovay sequence. Theta alpha is a limit of Slim cardinals if and only if alpha is bigger than 0 and alpha is a limit ordinal. So from the perspective of Slim cardinals, you can analyze the theta alphas. Now you could ask between theta alpha and theta alpha plus 1 what happens in alpha is a limit. Now it could happen that theta alpha is the largest Slim cardinal below theta alpha plus 1. That can only happen if alpha is a limit, and that's a very strong theory, which we'll see again shortly. So from the point of view of Slim cardinals and the parent AD plus model, this is the whole story on the theta alphas. What about the Solovay sequence in large cardinals? Well, so again, we're going to assume AD plus V is LFP of R. Take the Solovay sequence. Suppose alpha is less than or equal to the length of the sequence, and that alpha is either 0 or not a limit ordinal. It's a bit annoying that 0 is a limit ordinal, but it is. Then the following hold: theta alpha is a Woodin cardinal in HOD. Let delta be the largest Slim cardinal below theta alpha. Then delta is a strong cardinal in HOD intersect V theta alpha. Okay, so we're trying to understand the Solovay sequence from the point of view of large cardinals in HOD. Well, the situation where alpha is a limit is a bit more mysterious. So again, let this be the Solovay sequence. Suppose alpha is less than or equal to omega, then the following are equivalent. Theta alpha is a Woodin cardinal in HOD. Alpha equals 0, or alpha is a successor ordinal. This is a converse to the previous theorem. So if you look at the Solovay sequence and you ask which theta alphas can be Woodin, can only be theta 0 and the successive theta alphas. No non-zero limit theta alpha can be a Woodin cardinal. Okay, so that's the story for successors. For limits, as I said, it's more complicated. The conjecture, the theta alpha conjecture, assume AD plus and V is LFP of R, suppose delta is less than or equal to theta, then the following are equivalent. Delta is a theta alpha for some limit ordinal. That's one. And the conjectured equivalence is that delta is a limit of Woodin cardinals in HOD, and for all kappa less than delta, kappa is not less than delta strong in HOD. So this conjecture would characterize the theta alphas for alpha limit combinatorially in terms of the large cardinal structure of HOD. Well, there's a weak version of this where we condition on Slim cardinals, call that the weak theta alpha conjecture. So AD plus V is LFP of R. Suppose delta is a limit of Slim cardinal, so that's a feature delta has in the AD plus model. Then the following are equivalent. This is the conjecture. Delta is theta alpha for some limit ordinal alpha bigger than 0, and delta is a limit of Woodin cardinals in HOD. So this conjecture is saying that if you borrow from V the predicate which identifies the Slim cardinals, then you can pick out the theta alphas for limit alpha. They're simply the delta which are limits of Woodin cardinals. Okay, so this is a version of the theta alpha conjecture restricted to limits of Slim cardinals. And again, it's just a version. There are other versions one could do. So what about the case when there's a largest Slim cardinal? So Paul has mentioned this. In fact, if you assume AD plus DCR, the following are equivalent. AD plus, and the set of Slim cardinals is closed below theta. Remember, I said the closure of the Slim cardinals below theta was a consequence of AD plus. That's actually equivalent to AD plus. Well, if you know that the Slim cardinals are closed below theta, there's either a largest Slim cardinal or every set is Slim. Okay, so, and that's the theorem. Suppose now AD plus DCR, the following are equivalent, not ADR plus AD plus, and there's a largest Slim cardinal. Now the models of AD plus, which satisfy V as LFP of R, and I have a typo there, missing a parenthesis, and not ADR, and in which the largest Slim cardinal is on the Solovay sequence, are the LSA models of AD plus, and these have been studied quite a bit by Sargent. LAS is largest Slim axiom. So if you have a largest Slim cardinal, it may or may not be on the Solovay sequence. Okay, so if it is on the Solovay sequence, then theta is the last member of the Solovay sequence of that model, and there are no Slim cardinals in between. So this is much stronger than ADR and theta regular. Okay, so we have the theta alpha conjecture. It has a number of consequences, and we could try to verify those as evidence for the theta alpha conjecture. So assume V is LFP of R and ADR does not hold. Well, so we know that let delta be the largest Slim cardinal. We know that exists. Let's assume the weak theta alpha conjecture. Then the following are equivalent. Delta is a limit of Woodin cardinals in HOD, and delta is equal to theta delta on the Solovay sequence. Okay, and in fact, that's a theorem. So assume AD plus V is LFP of R, and ADR does not hold, but delta be the largest Slim cardinal, then this predicted consequence is actually true. Following our equivalent, delta is a limit of Slim cardinals in HOD, and delta equals theta delta. Okay, so this has, remember, we were going to look at large cardinals in HOD, so this has an interesting corollary. Assume V is LFP of R, and that ADR does not hold, so that there's a largest Slim cardinal. Suppose there's a Woodin cardinal in HOD above delta, and that should have been below theta, above delta and below theta, because theta is Woodin, then delta is theta delta. And the reason is that delta is strong up to theta. So if there's a Woodin cardinal between delta and theta, by the strength of delta and HOD, delta would have to be a limit of Woodin cardinals. Okay. Now this proof, the proof of this theorem, which uses the derived model theorem in Adplus machinery, adapts to actually prove the weak theta alpha conjecture. So assume Adplus and V is LFP of R. Suppose delta is a limit of Slim cardinals, and the following are equivalent. Delta is theta alpha for some limit alpha. Delta is a limit of Woodin cardinals in HOD. So if you focus on the limits of Slim cardinals, there's a simple characterization of which of those are on the Solovay sequence. Okay. Now, I want to say something briefly about V is LFP of R versus V of L of A in R for a set of reals. Paul's talked about that distinction quite a bit. In L of A and R, you can never have uniformization, so you can never have ADR. Suppose gamma is less than theta, then there is a set of reals such that gamma is less than the theta of L of A and R. And if you take HOD up to V theta A, that's HOD, the HOD of V up to V theta A is the HOD of L of A and R intersect V theta A. So you can catch any rank. So this says that if you assume AD plus and V is LFP of R, for the question of which sigma 2 expressible large cardinal axioms, say, which imply measurability, can hold in HOD, we can arguably reduce to the case that V is L of A and R for some A. And that just simplifies things, right? Because if that sigma 2 sentence held in HOD, it would be witnessed by something below theta, and then we could get this A. So perhaps we should assume large cardinals exist in V and just look for such sets A. And we'd like to narrow the search, and that takes us back to the universally bare set. So let me remind you what those are. Subset of Rn is universally bare for all topological spaces omega, for all continuous functions from omega to Rn. Rn is, say, Euclidean space here, or bare space, it doesn't matter. The preimage of A by pi has the property of bare in the space omega. So this is a kind of universal property in V. You have to look at arbitrarily large spaces. So the universally bare sets is not a local property in general. What? Oh, okay. Okay. Well, there's another definition which isn't. So what's the real definition? The real definition is for every lambda, there's there are two trees on lambda, one of which projects to A and one of which projects to the complement of A. Okay, that's trivial in ZFC, but those trees project to forcing extent to complements for all forcing notions of size less than lambda. So you have a way of representing A as a Suslin co-Suslin set by trees that still project to complements after you do forcing. This is the cosmetic version. Universally bare sets have the property of bare. Just take pi to be the identity. Using the measure algebra, universally bare sets are Lebesgue measurable. They have all the regularity properties associated to forcing. So they look like a really interesting class. But if you make no additional assumptions, they are not closed at all. If you assume V is equal to L, then every set of reals is the image of a universally bare set by a continuous function. So in L, even though the universally bare sets have all these regularity properties, they're just one step away from all sets of reals. But if we bring in large cardinals, that's no longer the case. So if you assume there's a proper class of Woodin cardinals and A is universally bare, then every set in L of A and R intersect P of R is universally bare. So the universally bare sets are not only closed under continuous images, they're closed under constructibility. Again, assume there's a proper class of Woodin cardinals. The Martin-Steele theorem shows that if A is universally bare, then A is determined. So these are determinacy models. And Steele showed that if A is universally bare, then A has a universally bare scale. Put that all together, and we get that if there's a proper class of Woodin cardinals and A is universally bare, then L of A and R is a model of AD+. And this is part of the reason for looking at AD+, that the canonical models of determinacy that you get from large cardinals are AD+ models. Okay, so now we can define the axiom V is ultimate L. Let me just define it. The axiom is there's a proper class of Woodin cardinals for every sigma 2 sentence phi. If phi holds in V, then there's a universally bare set A such that the HOD of L of A and R models phi. So in the context of V is ultimate L, if you have a sigma 2 expressible large cardinal axiom, then it has to hold in the HOD of L of A and R for some AD+ model L of A and R, and much more. So this is an example where, where one can define a candidate for V as ultimate L without knowing how to build the model. And the reason is we have these canonical determinacy models, and within these canonical determinacy models, we have a canonical construction, HOD. And those should be canonical fine structure models, and they are known to be fine structure models in many instances. So one's doing an end run around, instead of saying V is ultimate L, saying I am an ultimate L, and here's the 1,000-page construction. It's just a simple axiom. You could do the same for L, and you can express V is equal to L by the reflection of sigma 2 sentences into test models, and you don't need to use the L alphas for that. You just use minimal models. So because of the formulation of the axiom V is ultimate L in terms of AD+, which is lurking in the background here, one can couple into AD+ theory and get consequences of this axiom. And there's a rich AD+ theory to mine. So, some consequences of V is ultimate L. One is CH holds. That's scale sigma 2, 1 in the fine structure in the AD+ setting. A little bit harder is assume V is ultimate L, then V is equal to HOD. What about the universally bare sets in the setting of V is ultimate L? So assume V is ultimate L, let gamma infinity be the collection of all universally bare sets, then they are not closed. Gamma infinity is not P of R intersect L of gamma infinity in R. In fact, if V is equal to ultimate L, then the axiom of choice holds in L of gamma infinity in R. And this is the generalization to the axiom V is ultimate L of the fact that if V is equal to L, then there's a sigma 1, 2 well ordering of the reals. So if you assume V is ultimate L, there's a canonical well ordering of the reals. And that gives you a well ordering of the universally bare sets because of the nature of the model. What about the axiom V is ultimate L enforcing? Well, the intuition that fine structure models are L-like is not entirely accurate. If M is a model of ZFC as an iterable Mitchell-Steele model, and there's a Woodin cardinal in M, then M is actually a generic extension. That's a very L-unlike property. Any iterable Mitchell-Steele model is a non-trivial generic extension of, in fact, another iterable Mitchell-Steele model. And this is quite general. It holds for the non-strategic iterable models at the finite levels of supercompact. So there's an extension of the Mitchell-Steele theory to the finite levels of supercompact, and this theorem still holds. Of course, we don't yet know that those models exist. Put that aside. But if you assume V is ultimate L by coupling into AD+ theory, you can show that V is not a non-trivial generic extension of any inner model, which is what one would expect of any genuine L-like axiom. And that's related to the proof that if you assume V is ultimate L, then V is equal to HOD. Okay, so I want to just quickly review omega logic and the omega conjecture. So I'm going to do this on the next 3 slides. First, I have to define validity in omega logic. T is a theory in the language of set theory. Phi is a sentence. So phi is omega valid from T if for all generic extensions V of G of V, and for all alpha, if V of G alpha models T, then V of G alpha models phi. Now headed toward the definition of the proof relation for omega logic. That involves a universally bare set, so I need to say how they will be used. Suppose A is universally bare and M models EFC as a countable transitive set. Then M is A closed if A intersect M bracket G is in M bracket G for all G's such that G is M generic for some partial order in M. So M is A closed if A intersect M is in M, but that's also true for all the generic extensions of M. Okay? Now, in some cases, this is trivial. If A is finite, every M is A closed. There's a stronger notion of A closure, but for the purposes of defining the proof relation of omega logic, it doesn't matter which notion you use. So what's the proof relation? The idea is that the universally bare sets are the proofs. So suppose there's a proper class of Woodin cardinals, then T proves an omega logic phi if there's a universally bare set A, and such that M thinks T phi is omega valid for T for all countable transitive M modeling ZFC such that T is an M and M is A closed. So the idea is A is really the proof, and if you see the proof, you see the validity relation. Now, this is actually a very nice proof system in the sense that we have the wage hierarchy, so we actually have a notion of length of proof, and you can do Gödel sentences and things like that, but I'm not going to discuss any of that. So that's the provability relation. There's a soundness theorem that if T proves phi in omega logic, then phi is omega valid from T, but it's open the other way, and that's the omega conjecture. So and I'm just going to deal with the empty theory now, or a recursive theory if you want. Suppose there's a proper class of Woodin cardinals. The omega conjecture asserts that for all sentences phi is omega valid if and only if phi is omega provable. It's just the Gödel completeness theorem for omega logic, and it's open. All right, so what's the third part? The generic absoluteness of omega validity. This is a surprising theorem if you haven't seen it. Suppose you have a proper class of Woodin cardinals and T is a theory, phi is a sentence, then the following are equivalent. Phi is omega valid from T, and that's true in all forcing extensions of phi. So why is this surprising? This is sometimes called the sigma 2 resurrection theorem. Corollary of this is that if you have a proper class of Woodin cardinals and you have a sigma 2 sentence that's true in V, then it's forcible over any generic extension of V. So why is that surprising? Well, first, it's false in L, right? It's a sigma 2 sentence to say every real is constructible, but you're not going to force that over a generic extension of L if you've added a Cohen real, for example. So why is sigma 2 resurrection surprising? Imagine we're in a V with a proper class of Woodin cardinals and a rank to rank. Okay, so the existence of a rank to rank embedding is sigma 2. So we've got our rank to rank and these proper class of Woodin cardinals. So we have a sigma 2 sentence true in V, namely there's a rank to rank. So now collapse that rank to rank to be countable. You no longer have a rank to rank embedding. You just have a proper class of Woodin cardinals. But sigma 2 resurrection says by forcing you can recreate the rank to rank embedding. Where did that come from? That seems like that shouldn't be true. but it is. All right, so omega validity is generically absolute for set forcing. If you use AD+ theory, the proof relation, omega provability, is also absolute. That needs to scale sigma to 1 in the basis theorem. So the validity notion and the proof notions of omega logic are absolute. So as a corollary, the omega conjecture is absolute. So if you have a proper class of Woodin cardinals, then the following are equivalent. The omega conjecture holds in V, and 2, it holds in all generic extensions of V. So it's a feature of V, true or false, which is generically invariant. So one would expect to resolve it from large cardinals. So you would expect to resolve it, for example, from V as ultimate L. That's going to be the rest of what we're talking about. So I have to define another conjecture, the theta zero conjecture. Assume when you don't know how to prove a theorem, you just introduce a conjecture and then prove the theorem from the conjecture. It's a great way to generate pages. So the theta zero conjecture, assume AD plus V is LFP of R. The conjecture is that provably theta zero is the least Woodin cardinal of HOD. Is there any evidence for this conjecture? Well, there's pretty strong evidence. Assume AD plus V is LFP of R, then for a Turing cone of X, theta zero is the least Woodin cardinal in HOD sub X. Now, when you define theta zero, that was a soup of the lengths of the OD pre-will orderings. Using real parameters, you get the same ordinal. So what this is saying is that if you relativize to a real on a cone, then the theta zero conjecture is true. So that's some evidence that it should be true. Now, if you assume the theta zero conjecture, now that's a number theoretic statement because a conjecture says provably, then if you assume V is ultimate L, the omega conjecture holds. So if the theta zero conjecture is provable, V is ultimate L must imply the omega conjecture. Okay, but maybe we don't need the full theta zero conjecture, and there is an approximation to the theta zero conjecture. This is a relatively recent result. Assume AD plus V is LFP of R. Well, then there's at most one Woodin cardinal in HOD below theta zero. Now, theta zero is Woodin in HOD, and the theta zero conjecture says it's the first. This theorem says it can be at most the second. And there's another version of the theta zero conjecture. I'll call that the theta alpha plus omega theorem. Assume AD plus V is LFP of R. Let this be the Solovay sequence. Suppose alpha is equal to 0 or alpha is equal to beta plus 1, a successor for some beta less than omega. So theta alpha plus 1 is less than or equal to theta. Then the following are equivalent. Theta alpha plus omega is less than or equal to theta. There are omega many Woodin cardinals in HOD above theta alpha. So this is kind of the theta omega version of the theta zero conjecture. For example, a corollary of this is that assuming AD plus and V is LFP of R, theta omega is always the omega-th Woodin cardinal in HOD. So the theta omega conjecture is actually true. It's just there might be at most one Woodin, there might be some Woodin cardinals in between the theta ends. Okay, so applications of the theta zero theorem. Well, the theta zero theorem, the fact that you have at most one Woodin cardinal below theta zero, that's enough for the proof of the omega conjecture from V is ultimate L. So that's the main application. Assume V is ultimate L, then the omega conjecture holds, which is what I was headed for. There's another corollary which is amusing, and that's what I'll end with, and it gives a simple reformulation of the omega conjecture which avoids having to define the proof relation. So to state this, I want to introduce some notation so I can fit everything on one slide. If V is a pi2 sentence, then we'll say that phi is this, which I'm not, this just says phi holds in all generic extensions of V. So this is just if and only if Zermelo, phi is omega valid from Zermelo holds in V. It's just, this is too long to write as opposed to this. So we're just looking at the pi2 sentences which hold in all generic extensions of V. That's all I want from this notation. Okay, so now we're going to look at the axiom V is ultimate L versus the omega conjecture. So here's the theorem. Assume there's a proper class of strong cardinals and a proper class of Woodin cardinals. That's stronger than a proper class of Woodin cardinal. Then the following are equivalent. The omega conjecture, and that involves the proof relation. And then here's the reformulation that doesn't talk about the proof relation. There's a universally bare set A with infinitely many Woodin cardinals and the HOD of L of A and R, such that for all pi2 sentences phi, phi is true in all generic extensions of V, if and only if HOD of L of A and R restricted to theta thinks phi is true in all generic extensions of V. So it's a resemblance of V to HOD of L of A and R restricted to the theta of L of A and R. And you have to do the restriction because HOD of L of A and R is L of a set, so it knows there's a set whose sharp doesn't exist, and that's a sigma 2 statement. So you have to do this restriction here. Okay, so that's kind of a nice reformulation of the omega conjecture. The amusing thing is if you make one change in this statement, you get the axiom V is ultimate L. And so in this view, the axiom V is ultimate L looks like a minor syntactic perturbation of the omega conjecture. So here's the theorem. Suppose there's a proper class of strong cardinals, proper class of Woodin cardinals, and the following are equivalent. The axiom V is ultimate L, which I defined. There's a universally bare set A with infinitely many Woodin cardinals and the HOD of L of A and R. Again, for all pi2 sentences, the change here is it's just satisfaction instead of omega validity. Okay. So you just, so you just take the statement of the omega conjecture, you erase those omegas, and what you get is an equivalence for the axiom V is ultimate L. So it's just an amusing consequence of the theorem. So I said I would end early, and this is the last slide, and I'm done. So thank you.
Are there any questions? Yeah, can you explain why you
so the original, this is going to sound like I paid him to ask this question. The original formulation for V is ultimate L was to reflect sigma 3 sentences into these models. And the idea is these models should resemble V more and more. So we reflect sigma 3. And one reason for doing that is whatever version of V is ultimate L you use, if you're reflecting more complicated sentences into canonical models, it's easier to get consequences of that. So if you impose reflection of sigma 3 sentences, getting the omega conjecture is easy. Whereas by just reflecting sigma 2 sentences, one had to go through a lot more work, for example, to get the omega conjecture. So why abandon sigma 3? Well, if you assume HOD of L of A and R has a feature that it can be analyzed as the HOD of L of A and R is, as a directed system, admits a directed system analysis, which we believe, then you can show that in the HOD of L of A and R restricted to theta, there cannot be a supercompact cardinal. Well, the existence of a supercompact cardinal is a sigma 3 statement. So if you state V is ultimate L in terms of sigma 3 sentences, and you assume the 80 plus models are well behaved, there can't be a supercompact cardinal in V. And that's why.
Soundness direction,
Yeah, but that's a separate issue. That's a separate issue. No, soundness holds for both directions, the way I stated omega logic, because omega logic is talking about... No, but omega logic only talks about satisfaction in the V alphas. Yeah, no, if you try to do omega logic with sentences in V, of course that doesn't work. This is a separate issue. In other words, the intuition was you have HOD, you have all these 80 plus models that are canonical. And you choose the sets from within the universally bare sets. An appealing picture would have been that if gamma is powerful enough, then you could reflect any sentence of V into the HOD of L of gamma and R restricted to the theta of L of gamma and R. And that these models should resemble V more and more as you impose conditions on gamma. And the point is that that's not true because you can't have a supercompact in the model. Same thing works for L of... So you can show that if a sigma 3 sentence holds in the HOD of L gamma of R truncated at theta, then it reflects into the HOD of L of A and R truncated to the restriction of theta. It's the variation of that theorem I stated. So if you're going to reflect sigma 3 sentences, you might as well reflect into L of A and R, because if you can reflect into L gamma of R, you can reflect into L of A and R. The tension is there's a conjecture. Remember, if you can't prove a theorem, you make a conjecture. So there's the HOD ultrafilter conjecture. It's an 80 plus conjecture. The conjecture is assume 80 plus V is LFP of R. Go to HOD and take a countably complete ultrafilter. Then the conjecture is that that's a countably complete filter in V. That the countable intersections are non-empty. Now, by theorem of Steele, if you have the direct system analysis, you'll verify the HOD ultrafilter. It's true in L of R. The HOD ultrafilter conjecture is true in L of R. It's true in all the HODs of all the 80 plus models which we can currently analyze. Okay? If the HOD ultrafilter conjectures holds in an 80 plus V is LFP of R model, then no cardinal of HOD can be supercompact up to theta. In fact, it can't even be supercompact up to the next cardinal of the determinacy model. So supercompactness has to be a really local phenomenon if you have the HOD ultrafilter conjecture. And that's why you don't reflect sigma 3 sentences. So, again, in the scheme of what should be true, the HOD ultrafilter conjecture should surely be true. Otherwise, it says there are 80 plus models whose HOD we cannot analyze by the techniques that we currently analyze HOD. So that would be somewhat surprising. So you can't hope to reflect sigma 3 sentences. So one is forced to restate V as ultimate L in terms of the reflection of sigma 2 sentences. And that makes all the theorems, as I said, a bit more complicated to prove. And the one that was quite a bit more complicated was the omega conjecture. If you can reflect sigma 3 sentences, getting the omega conjecture is easy. Okay. So I should point out the large cardinal structure of HOD above, in L of A and R, above the largest Slim cardinal, is a little bit mysterious. And especially once you get into long extenders. Anyway, so supercompactness as a feature of HOD can only be extremely local. No cardinal of HOD can be supercompact up to the next determinacy cardinal. So that's really tiny bands where supercompactness can hold. And so there's no way a cardinal less than theta is going to be supercompact up to theta, because theta is a limit of 80 cardinals. So it's a very local, banded, and so that's why one's stuck with sigma 2 sentences. Long answer to a simple question. Sorry. The slides will be available once I correct them, and I'll give them to both the slides for today and last week.